guys, I'm Kelly Martin and I'm here to talk to you guys about Dalton's law of partial pressures. The first assumption made in Dalton's law of partial pressures is that all gases are ideal. Now what does that mean? Ideal gases. It means that gases have 1, no volume, and 2, they experience no intermolecular forces. Now, are these assumptions true? Not necessarily, because gases do have volume and they do experience IMFs. But these assumptions have to be made in order for the equation, Dalton's law of partial pressures, to work. Now let's look at the actual equation. Let's write it down. So the total pressure of all the gases is equal to the partial pressures of each individual gas. So gas 1 plus the pressure of gas 2, and so on. And how does this equation connect to the ideal gas assumptions? 1, each of these partial pressures here are pressures that the gases would experience if they were the only gas in the container and if they had no volume. So their momentum was continuous. So since that's not true, some of these values that you get might not be accurate in real life. Now let's look at a problem. Let's say that a chemist adds solid zinc powder to a solution of hydrochloric acid to initiate the following reaction right here. So let's say maybe the chemist inverts a test tube and immerses the open mouth of the reaction beaker to collect the hydrogen gas that bubbles up from this solution. At the end of the experiment, the water levels within the tube and outside of the tube are equal. So that means that the pressure inside of the tube is equal to the pressure of the atmosphere around it in the lab. So that means we know the total pressure inside that tube is 101.35 kilopascals. And since the entire system is at standard temperature and pressure, that's 298 Kelvin and 101.35 kilopascals, we can then assume that the vapor pressure of water is going to be 3.17. So, using that information, we can actually solve for the partial pressure of H2 gas right here. We know that the entire system has a total pressure of 101.35 kilopascals. Now let's set that equal to the partial pressure of hydrogen plus the partial pressure of the vapor, water vapor. Now, since we know that this is 3.17, we can plug this in right here and solve, do some quick maths to find that the pressure of H2 is equal to 98 kilopascals. A very common trick in many chemistry courses is the addition of an inert gas to a rigid system. So let's say we have a total pressure here consisting of, let's say, hydrogen, oxygen, and nitrogen. Now, if we were to add an inert gas, such as argon, to the system, what would happen to each of these values? Would the total pressure increase or decrease? Would each individual partial pressure increase or decrease? Well, what will happen is that each of these partial pressures will remain constant. O2 will be equal to O2, H2 will be equal to the pressure of H2, all of them will not change. Except on the end right here, we now have a new partial pressure, and that is the partial pressure of argon. Now we set it equal to our total pressure. Since none of these values right here are changing, except for the argon value, that means to set both of these sides of this equation to be equal, this total pressure right here would have to increase. So when inert gas is added to a system, the partial pressures are not affected, but the total pressure is.